Hello, Algebra 2 folks, and welcome to 7.3. Let's talk about E. So you're going to learn about E today. So you're going to need your notes, a calculator, a pen or a pencil, and a couple pieces of graph paper. If you don't have graph paper, you can go to my website, and on the left-hand side under graph paper, you can click and download and print off as many pieces of graph paper as you need. All right, so let's go ahead and talk about E. But before we can talk about E, let's remember pi. So do you remember from geometry what pi represents? Well, pi represents a number. It's approximately 3.14159. I can keep going on and on and on forever. It's an irrational number that just keeps going. It never repeats, it never terminates, and pi is represented by the number 3.14. Now, if I were to ask you if you could simplify expressions containing pi, I would hope you could say yes. In geometry, you had to leave things in terms of pi all the time. So if I had 5 pi quantity squared, what would that mean? That would mean, that would mean 5 pi times 5 pi. 5 pi times 5 pi? Well, that's 25 pi squared. How about 15 pi to the 5th over 20 pi to the negative 1? Well, 15 over 20, that reduces to 3/4. And anytime I have a negative exponent, I would move it up, and I would get 3 pi to the 6th over 4. Now, also in geometry, you left things in terms of pi, but you also evaluated with pi. So you would take out your calculator and type in 25 pi squared, and you could get a number, approximately something. So pi was used in geometry, and we were able to simplify expressions with pi and evaluate pi. Today, you're going to learn about Euler's number. Euler's number is E. And just like pi, E represents a number. It's approximately 2.71828. So it's approximately 2.72. So E is one of the most important numbers in mathematics, along with pi and I, and we'll see E quite often in math, in the higher level maths. Okay, so knowing that we know what E is, and remember we're going to say that it's approximately 2.72, okay, we will use that number as Euler's number. Okay, so could we simplify the expression with an E? Well, of course. If you remember how you did pi and you remember the exponent rules, we can do the same thing with E. So 2 times 6 is 12, and e to the negative third and e to the 5th, if I have a multiplication, I would add the exponents and get e squared. Okay, let's write down the second problem here. This says 24e to the 8th over 4e to the 5th. 24 over 4 would be 6, and e to the 8th over e to the 5th would give me e to the 3rd. So I just simplified using e's. Could I also evaluate them? Of course. If you have a graphing calculator or a scientific calculator in front of you, most of those have an E key. It's usually above a key, okay? So if you're looking for it, look for the E. If you don't have an E on your calculator, you could just go ahead and type in 12 times 2.72 to the power of 2. And you would get approximately 88.67. Now we could do the same thing for 6e to the 3rd. If you have an E button, you can type 6 times e to the 3rd in your calculator, or you could type 6 times 2.72 to the 3rd power, and you would get approximately 120.51. Okay? So that is how we would simplify or evaluate using E. Okay, let's simplify this expression. So this says 4e to the 2x, all of that to the third power. Now don't get scared because you see the x there, okay? Still going to use the exponent rules. Remember what a power of 3 means. It means everybody gets the power of 3. So this would be 4 to the third e. We'd multiply 2x times 3 and we'd get 6x. Now 4 to the third is 64, e to the 6x. Now we can't evaluate this unless we know what x is. And if we don't know what x is, we would just leave it 64e to the power of 6x. What else can we do with e? Well, it just so happens that we can also graph. E is called a natural base. It's basically a base, okay? So this kind of looks like an exponential function to me. And because x is in the exponent, okay? And we are going to graph this using e. Okay, well this says y equals e to the x. I have x in the exponent, so remember your domain would be all reals. So I'm going to use -2 to 2, okay? And in your calculator, you're going to type in e to the -2, and you are going to get 0.14. If you type e to the -1, you'll get 0.4. E to the 0 will give me 1. E to the 1 is 2.72. And e to the 2 is 7.4. All right, and I'm going to graph this. -2.14, -1.4, 0, 1, 1, 2.72, and 2, 7.4. Ooh, what does this remind you of? Exponential growth. And it would be exponential growth because e is 2.72. And remember, when the base is greater than 1, it's a growth. So this is just like exponential growth. All right, what would the range be? The range would be anything greater than 0 because the asymptote, in this case, okay, would be y equals 0, just like an exponential growth graph. There's no shifting up or down here, so the asymptote is 0. All right, let's graph another natural base exponential function. But this time I have y equals e to the -x plus 1. All right, but x is still in the exponent, so I'm still going to use -2 to 2. So this is going to be x such that x equals all reals. My asymptote now is going to be 1 because I'm shifting it up 1. Okay. And then let's figure out what our range is going to be by filling out the rest of our table. So let's do e to the -2. Well, that's +2 plus 1. That's going to give me 8.4. If I do e to the -1, that's a +1 plus 1. That would give me 3.7. Then if I do e to the -0, that's just like e to the 0. That's 1 plus 1, which will be 2. If I do e to the -1 plus 1, that's going to give me 1.4. And e to the -2 plus 1 is going to give me 1.14. So when I graph this, I get -2, 8.4, -1, 3.7, 0, 2, 1, 1.4, and 2, 1.14. Now, what does this remind you of? Hopefully, this reminds you of exponential decay. And why is this one decay? The reason why it's decay is because of that negative sign. That negative sign in front of x causes this graph to become a decay function. The range, because the asymptote is 1, the range is going to be greater than 1 because all of it is graphed above the asymptote of 1. So with ease, we can simplify them, we can evaluate them, and we can even graph them. That's all I have for E. We'll talk to you later.